This is the fourth lecture of the 5-lecture series on polarization. In the last lecture, which was the third one, we considered phenomena of double refraction, looked at dichroism, and studied the working of a Nicol prism. See, double refraction is a very typical phenomena of anisotropic crystals. We considered crystals of calcite and quartz. What happens in these, when a light beam is incident, there are two refracted rays, one the so called ordinary in the sense that it obeys Snell's laws of refraction, the usual one. The speed is same in all directions, the phase front is spherical. There is another refracted beam called the extraordinary beam, where the direction of propagation is different. It moves with different speeds in different directions. The result is that the phase fronts are ellipsoid of revolution about the optic axis. Optic axis is the axis of symmetry. The two beams, ordinary and extraordinary, both of them are plane polarized with vibrations in perpendicular directions. In the case of ordinary, the direction of vibration is perpendicular to the plane containing the propagation direction and the optic axis. In the case of extraordinary beam, these vibrations are in the same plane. Both of these beams are plane polarized. We also studied dichroism. You see, dichroic crystals like tourmaline, they are also doubly refracting with the additional property that they have a very markedly unequal absorption of the ordinary and extraordinary beams, with the result that the emergent beam is plane polarized to a pretty good degree. Then we considered Nicol prism. Here the ordinary beam is totally reflected, things are arranged in such a way, and the result is the emergent beam is plane polarized, and we have got a polarizing device. In the present lecture, which is the fourth one, we shall consider interference of polarized light. We shall analyze working of quarter and half wave plates of doubly refracting crystals. We shall consider different types of polarization and their analysis. Interference of polarized light. We have already studied how a plane wave incident on a doubly refracting crystal splits up into two waves within the crystal, each characterized by a certain state of polarization. Their directions of polarization can be ascertained experimentally. The result of their superposition can also be analyzed experimentally. Now, we will consider normal incidence of a plane polarized beam on a calcite crystal, which is cut such that the optic axis is parallel to the surface of the crystal. The propagation here is perpendicular to the optic axis. We will study the state of polarization of the beam emerging from the crystal. Let us make the propagation direction as the x axis, just choose it like that. We will assume the z axis to be along the optic axis, which is the axis of symmetry in the crystal. Now, we know that if the incident beam is y polarized, the beam will propagate as an ordinary wave and the extraordinary wave will be absent. In this case, the vibrations are in the zx plane. Similarly, if the beam is z polarized, the beam will propagate as an extraordinary wave, and the ordinary wave in this case will be absent. Let E naught be the amplitude of the electric vector associated with the incident beam, and let it make an angle phi with the z axis, which is the optic axis as we have chosen. Such a beam can be assumed to be a superposition of two linearly polarized beams vibrating in phase at the entry point of the crystal and polarized along the y and z directions with amplitudes E naught sin phi and E naught cos phi respectively. The z component, whose amplitude is E naught cos phi, passes through as an extraordinary beam propagating with the wave velocity c by n e. Here the vibrations are parallel to the optic axis. The y component, whose amplitude is E naught sin phi, passes through as an ordinary beam propagating with the wave velocity c over n0. Here the vibrations are perpendicular to the optic axis, also perpendicular to the propagation direction. Now, since n e is not equal to n0, the two beams will propagate with different velocities, but there will not be any separation in this case because they are incident normally, and as such when they come out of the crystal, naturally they will not be in phase. Consequently, the emergent beam, which will be a superposition of these two beams, will be in general elliptically polarized. We have discussed this case in the earlier lecture as well. The arrangement thus provides an experimental setup, and that is the main thing. We are discussing the experimental setup now to bring about the superposition of two perpendicular vibrations of different amplitudes and arbitrary phase difference, which was considered earlier as I pointed out. You see, the different amplitudes can be obtained by varying the angle phi, and the phase difference can be varied by varying the thickness of the crystal. Let us now analyze and study this setup in detail. Let the plane x equal to 0 represent the surface of the crystal on which the beam is incident. X is equal to 0 plane is the incident plane. The y and the z components of the incident beam now can be written in the form E y is equal to E naught sin phi, that is the amplitude, cos k x minus omega t, E z equal to E naught cos phi and cos of k x minus omega t. The propagation is along the x axis. K is equal to omega by c, it represents the free space wave number. At x is equal to 0, which was the entry point, we have E y at x is equal to 0 equal to E sin phi cos omega t, and E z at x is equal to 0 is equal to E naught cos phi cos omega t. Inside the crystal, the two components will be given by E y equal to E naught sin phi cos of NO kx minus omega t is for the ordinary, NO is the refractive index for the ordinary, and Ez equal to E naught cos phi and Ek cos of and Ekx minus omega t, Ne is the refractive index for the extraordinary. So, this is for the extraordinary wave. If the thickness of the crystal is d, then after traversing a distance equal to d, at the emerging surface, we will have E y equal to E naught sin phi cos of omega t minus theta 0 and E z equal to E naught cos phi cos of omega t minus theta e, where theta o is equal to n 0 k d and theta e is equal to n e k d. By appropriately choosing the instant t equal to 0, these components may also be written as, in a simpler way, E y equal to E naught sin phi cos of omega t minus theta and E z equal to E naught cos phi cos of omega t, where theta is the difference between theta o minus theta e, which is equal to k d times n o minus n e, which is equal to omega by c times n o minus n e times d, which is equal to 2 pi by lambda naught into n e minus n o times d. This represents the phase difference at the emergence between the ordinary and the extraordinary beams. Lambda naught is the free space wavelength of the light used. The resultant of these two components can be obtained by eliminating t between them, and that gives E y upon E naught sin phi is equal to E z upon E naught cos phi times cos theta plus the square root of 1 minus E z upon E naught cos phi squared times sin theta. We can rearrange that, and that gives E y upon E naught sin phi minus E z upon E naught cos phi times cos theta, which is equal to the square root of 1 minus E y upon E naught cos phi squared times sin theta, or E y square upon E naught sin phi squared plus E z square upon E 0 cos phi squared minus twice of E y E z upon E 0 square sin phi cos phi times cos theta equal to sin square theta. This is the equation of an ellipse, which represents the general state of polarization resulting from the superposition of two perpendicularly polarized, plane polarized beams traveling in the same direction with unequal amplitudes E naught sin phi and E naught cos phi and an arbitrary phase difference theta. Various cases corresponding to different values of theta were in a general way discussed in the earlier lecture. We shall now in this lecture consider in detail special situations where theta equal to 2 pi or pi by 2 and phi equal to 45 degrees, pi by 4, and how to obtain them, how to realize them in the lab performing the experiment. That is the main idea of today's lecture. Let us consider these full, half and quarter wave plates. Remember, we are talking about a crystal plate where the optic axis is in the plane of the crystal and the propagation is perpendicular to the optic axis and the incidence is normal under those conditions. If the thickness of the crystal is such that theta equal to 2 pi, 4 pi, 6 pi, I mean 1 complete vibration, 2 complete vibrations, 3 complete vibrations, the emergent beam will have the same state of polarization as the incident beam. Such a crystal plate is called a full wave plate. Such a plate, however, is not very useful. If the thickness d of the crystal is such that theta equal to pi by 2, a quarter vibration, the crystal plate is called a quarter wave plate, usually abbreviated as QWP. A phase difference of pi by 2 implies a path difference of a quarter of wavelength, that is lambda by 4, between the ordinary and the extraordinary waves. Similarly, if the thickness of the crystal is such that theta equal to pi, the crystal plate is called a half wave plate, usually abbreviated as HWP. This plate corresponds to a path difference of half a wavelength, that is lambda by 2, between the ordinary and the extraordinary waves. Let us consider in detail the working of a quarter wave plate. Let us consider the case when theta equal to pi by 2 and the angle phi, which the electric vector of amplitude E naught of the incident wave makes with the z axis, which is the optic axis. Remember, the optic axis is the symmetry axis, and the propagation here is perpendicular to the optic axis. So, the angle phi is equal to pi by 4. Now, the y and z components of the incident wave have equal amplitudes, E naught cos of pi by 4 or E naught sine of pi by 4, they both of them are equal to E naught upon square root of 2, and the crystal introduces a phase difference of pi by 4 during the passage. The figure shows the progressive phase difference between the ordinary and the extraordinary beams as they travel in the crystal. In the beginning, they are in the same phase at the entry point. At emergence, at the other end of the crystal, after traveling a distance d, this phase difference in this case becomes pi by 4 as shown in the figure. Thus, for the emergent beam, we have Ey is equal to E naught upon square root of 2 times sin omega t, and Ez is equal to E naught upon square root of 2 cos omega t, which represents a circularly polarized wave, because Ey square plus Ez square is equal to E naught square by 2, which is the equation of a circle. In order to determine the direction of rotation, I mean the sense of rotation of the electric vector, let us consider the electric fields of the components initially at time t equal to 0, Ey is equal to 0 and Ez is equal to E naught upon square root of 2, and a little time later at t equal to delta t, Ey becomes equal to E naught upon square root of 2 times omega times delta t, and Ez is equal to E naught upon square root of 2 times 1 minus omega delta 2 squared by 2. The y component has slightly increased and the z component has slightly decreased. That is why the above values show that as the time increases, the electric vector rotates in the anticlockwise direction, and hence the beam is left circularly polarized LCP as shown in the figure. The passage through the quarter wave plate makes the initially plane polarized light with equal amplitudes. The quarter wave plate introduces a phase difference of pi by 2 of quarter vibration. The result is we get a left circularly polarized light. In order to introduce a phase difference of pi by 2, the thickness of the crystal plate should have a value given by the following relation. d is equal to c upon omega into n o minus ne times pi by 2, which is equal to lambda naught by 4 divided by n o minus ne. For calcite, NO is given by 1.65836 and Ne is equal to 1.48641. This is corresponding to a light of wavelength 589.3 nanometers, and substituting these values gives D is equal to 0.000857 millimeters. Thus, the calcite quarter wave plate at lambda equal to 589.3 nanometers will have a thickness of 0.000857 millimeters and will have its optic axis parallel to the surface. Remember, all the time the propagation is perpendicular to the optic axis and there is no separation between the two beams. Such a quarter wave plate will introduce a phase difference of pi by 2 between the ordinary and the extraordinary components. Note that Y polarized ordinary wave in calcite has a smaller wave velocity c over NO, and hence it is referred to as a slow wave, and the extraordinary wave is the fast one in calcite. Let us consider now a half wave plate. This is the case when the plane polarized beam is incident on a HWP half wave plate, so that the phase difference theta caused by the plate is equal to pi, half a vibration, path difference of lambda by 2. Again, let us take the inclination phi of the electric vibrations of the incident plane polarized beam with the optic axis, which we have taken as the z axis here, again equal to pi by 4. So, the ordinary and the extraordinary again have equal amplitudes. The crystal introduces a phase difference of pi. Let us not consider the quarter wave plate part at the moment. Thus, for the emergent light beam in this case, we have Ey is equal to minus E0 upon square root of t cos omega t, and Ez equal to E0 upon square root of 2 cos omega t. Note the minus sign which is appearing in the expression for Ey. This represents a plane polarized wave with the direction of polarization making an angle of 135 with the z axis. Remember, in the beginning at the entry point the angle was 45 degrees, now it is 135 degrees. In the beginning, again remember, they are in the same phase. This figure again shows the build up of the phase difference between the ordinary and the extraordinary. The phase difference ultimately becomes equal to 135 degrees. If we now pass this beam through a calcite quarter wave plate, the quarter wave plate introduces a phase difference of pi by 2. The emergent beam will be right circularly polarized as shown in the figure. Incident light with a plane polarized with angle of 45 degrees passes through a half wave plate, the phase difference becomes 135 degrees, passes through a quarter wave plate which introduces another phase difference of pi by 2, and the result is the light is right circularly polarized. So, this is what this figure shows: passage of a plane polarized light first through a half wave plate, which, as I said, introduces a phase difference of pi, and then through a quarter wave plate which introduces an additional phase difference of pi by 2, making a total of 3 pi by 2. Now, finally, at this stage, Ey is given by minus E0 upon square root of 2 sin omega t, and Ez is equal to E naught upon square root of 2 cos omega t. Eliminating t, we again get the equation of a circle. E y square plus E z square is equal to E naught square upon 2. Again, as we did earlier, in order to determine the sense of rotation of the electric vector E, consider the values of E y and E z at time t equal to 0. So, at time t equal to 0, E y is equal to 0 and E z is equal to E naught upon square root of 2. A little time later, at t equal to delta t, E y is equal to minus E naught upon square root of 2 times omega delta t, and E z is equal to E naught upon square root of 2 times 1 minus omega delta t square upon 2. The electric vector E has again increased, but in the other direction, and the Ez component has slightly decreased, and this shows that the electric vector now in this case rotates in the clockwise direction. This figure shows the electric vector of a progressing right circularly polarized beam. Now, on the other hand, if a left circularly polarized beam is incident normally on a half wave plate, the emergent beam will be right circularly polarized. You see, initial plane polarized light passes through a quarter wave plate, becomes a left circularly polarized light, passes through a half wave plate, becomes a right circularly polarized light. Only the intermediate state of polarization between the two plates is different here. First, as I said, the quarter wave plate introduces the phase difference of pi by 2, makes the light beam left circularly polarized, and then the half wave plate introduces an additional phase difference of pi, making a total of 3 pi by 2 as before, and making the light beam right circularly polarized. The thickness of the crystal plate for a half wave plate is given by, in a very natural way, d is given by lambda naught by 2 divided by NO minus NE. Let us now consider the analysis of polarized light. A plane wave can be characterized by different states of polarization, as we have seen during the course of this lecture. It may be any one of the following. It could be a linearly polarized light, B, it could be a circularly polarized light, C, it could be elliptically polarized light, and D, it may be just unpolarized. Or in addition to all these 4 cases, E, it could be a mixture of plane polarized light and unpolarized light. It could be a mixture of circularly polarized light and unpolarized light, or it could be a mixture of elliptically polarized light and unpolarized light. So, we have 7 different possibilities. One thing should be noted, to the naked eye, all these states of polarization will appear to be the same, absolutely no difference. We shall now study the procedure, what steps are to be taken for determining the state of polarization of a light beam. If we introduce a polarizer working here as an analyzer in the path of the beam, and we rotate it about the direction of propagation, then either of the following 3 possibilities can occur. You see, the incident light beam is there, which is to be analyzed. We pass it through a polarizer and we rotate the polarizer about the direction of the beam and watch what happens. First case, if there is complete extension at 2 positions which are 180 degrees apart of the analyzer, then the beam is plane polarized. This means we rotate it, we get a 0 intensity at some position, rotate it 90 degrees, becomes maximum, a further rotation of 90 degrees, again the intensity becomes 0. So, in a complete rotation there are 2 positions 180 degrees apart where there is a complete extension. Remember Malus law, and that shows that the incident beam is plane polarized. Number 2, if there is no variation of intensity, then the beam is either unpolarized. Again we have seen this thing earlier, if the beam is unpolarized and you pass it through a polarizer, we call it as an analyzer here, and rotate it, there is no variation in the intensity. So, the beam could be unpolarized, but we also know that the same thing will happen if the beam is circularly polarized or is a mixture of unpolarized and circularly polarized light. To analyze, differentiate between these two possibilities, that the light beam is unpolarized, circularly a mixture of unpolarized and circularly polarized. We now put a quarter wave plate in the path of the beam. So, the incoming beam, we allow it to pass through a quarter wave plate and again by an analyzer which is rotated as before about the direction of propagation. When we do this, 3 situations are possible. A, now there is no variation of intensity. The result is, this means the incident beam is unpolarized. The reason is a quarter wave plate does essentially nothing to an unpolarized beam. It was showing no variation when the analyzer is rotated. Even after passage through a quarter wave plate, the same situation will prevail. There will be no variation in intensity. So, that shows that the incident beam is unpolarized. B, if there is a complete extension at 2 positions 180 degrees apart, this means the original beam is circularly polarized. This is due to the fact that a quarter wave plate will transform a circularly polarized light into a plane polarized light. You see, the incident beam is circularly polarized means a combination of 2 perpendicular plane polarized light with a phase difference of pi by 2. The quarter wave plate introduces an additional phase difference of pi by 2, making a total of pi r 0. In both the cases, the emergent light becomes a plane polarized and there will be complete extension at 2 positions following Malus law. Okay, so, in case B clearly shows that the beam is circularly polarized. A third possibility C is if there is a variation of intensity, but without complete extension. Naturally, in this case the incident beam is a mixture of unpolarized and circularly polarized. Passage through the quarter wave plate does nothing to the unpolarized part of the beam, part of the mixture. Circularly polarized light becomes plane polarized. So, the result after passage through the quarter wave plate is something like a mixture of unpolarized and plane polarized. When we pass it through an analyzer and rotate it, there is a variation in intensity, but complete extension is not there. Now, we come to the third possibility. If there is a variation of intensity, but without complete extension, the incident beam could be either elliptically polarized, giving the same variation, or a mixture of plane polarized and unpolarized, or it could be a mixture of elliptically polarized and unpolarized. So, here again, the quarter wave plate is a very useful set, a very useful piece. We again put a quarter wave plate in the path of the beam with its optic axis parallel to the path axis of the analyzer at the position of maximum intensity. This is a change from the earlier case. We put the quarter wave plate all right in the path of the beam with its optic axis parallel to the path axis of the analyzer at the position of maximum intensity. This is followed by the analyzer, which is rotated again as before about the direction of propagation. 3 situations may occur. A, the elliptically polarized light will transform to a plane polarized light. Remember, elliptically polarized light, there is also a path difference of a quarter vibration quarter wave plate will introduce an additional quarter vibration. The result is the emergent light will become plane polarized, and one will get two positions 180 degrees apart of the analyzer where the complete extinction occurs. Malus law. Then the original beam is elliptically polarized. B, if complete extinction does not occur and the position of maximum intensity occurs at the same orientation as before putting the quarter wave plate, same position as before, the original beam is a mixture of unpolarized and plane polarized light. The case C finally, if the position of maximum intensity, again there is a variation, but the position of maximum intensity occurs at a different orientation of the analyzer. In this case, the original beam is a mixture of elliptically polarized and unpolarized light. So, these are the various steps which are needed to analyze the polarization, various polarizations of the light, the 7 cases which we have considered: the unpolarized, plane polarized, circularly polarized, elliptically polarized, or the mixture when you have unpolarized along with circularly polarized, or unpolarized along with plane polarized, or unpolarized along with elliptically polarized. Okay, so with this we have come to the end of the present lecture.